Today, we're going to talk about the Moivres Theorem. This is going to be a short, sharp, shiny one, and then I've got some practice tests ready to go. And then I suspect on Tuesday's lesson next week, we'll have a good chat about test content. We could do today, maybe after recess if you guys want to, but that's probably where I'm going to plant it for now. So this is the theorem here. We know we can express complex numbers in polar form, and so therefore we can distribute n, okay, by going like that, and cis n theta. This can be one that we prove as well. It's pretty simple to prove, but for now let's just stick with the rule. So if we have 3 cis pi on 6 squared, it's going to become 3 squared cis of 2 pi on 6. Okay, so in polar form, that would be 9 cis of pi on 3. And we can simplify this by converting it back to Cartesian form, can't we? Back to this complex number. So let's revise that quickly. We've got, what's it? Cos of pi on 3 plus pi sine of pi on 3. Okay, so that's going to be half plus I root 3 on 2. And so we've got, 9 on 2 plus, we do tend to, by convention, put the i's first, so it's not a major point of contention. Okay, we've got the next one here. Now you're looking at that and we could go, oh, we could apply the binomial expansion and expand that out forever. It would be very painful. All right, the quickest way to solve a problem like this is to convert it to polar form and then apply the Moivres theorem. So if we have 1 plus I root 3, if we want to convert it to polar form, we need the modulus. Okay, so the modulus is going to be the square root of the real component plus the imaginary component. All right, so that gives us root 4, which is 2. So the modulus is 2. And then we need the argument. And so we have here the argument is of z is inverse tan of root 3 over 1, which is, and sine of root 3 is pi on 6. Okay, so this one's going to be 2 cis of pi on 6 to the power of 5. Alright, so we've converted it to polar form, and then we've just substituted the polar form in, and now we can apply the theorem. That's going to be 2 to the 5 cis of 5 pi on 6. Alright, and if we want to convert that back to Cartesian form, so we have 2 to the 4 is 16, 2 to the 5 is going to be 32. We're going to have cos of 5 pi on 6 plus I sine of 5 pi on 6. Which is plus half. Okay, so let's have a go at applying that. It's pretty straightforward. Maybe later we can look at the proof if we're feeling so inclined. But for now, let's just have a bit of a look at this theorem.